Welcome back to ECE 442-542. Your first homework assignment is due tomorrow, and hopefully that is available until 11:59 p.m. tomorrow evening. Some of you have already turned that in. I don't know if it's complete or not. I haven't looked at that, but there are some that have deposited that in the Dropbox. You can put it, either give it to me today, you can turn it into my mailbox in the ECE building. I wouldn't wait until 11:59 and try to get it into the ECE mailbox. They may pull the gate down before that, but you can have access to that for a while. But the Dropbox will be open until 11:59 p.m. tomorrow evening. A week from that, homework 2 will be due. That is now available on D2L in unit number 2. And 2 weeks from today, you will be frantically scribbling down your answers to exam number 1. And I'll try to make a unit on D2L that maybe contains some information relative to exam number 1. At least I'll give you a list of topics that you can expect to attack in 2 weeks. I'm not sure I have old exams that are completely compatible. Maybe I'll just give you some old exams and leave it up to you to figure out which problems are consistent with this particular iteration of the course. That might be a good exercise for your studying. Today what I want to do is continue where we left off. Last time we'll talk about S-plane to Z-plane mapping, try to get a feel for where poles match in the S-plane to consistent or corresponding locations in the Z-plane. If I'm looking for a stable system, where am I looking in the Z-plane for my poles of a transfer function? Where do they need to be living, or where do they belong? And that I'm sure you picked up on the audio. But inside the unit circle, I hope, is what was stated. We will look at how to find a 1% settling time. That may have not been completely clear. I've answered a few of those questions during office hours. For a generic first-order difference equation, how can we compute a 1% settling time? We'll look at playing with the discrete time transformation from a difference equation into a frequency domain version, or a description that we can now get a transfer function for. That will then beg the question, can we create a Z transform like we created a Laplace transform in continuous time? So we'll then look at the definition of the Z transform, and we'll start computing the Z transform for some common waveforms. I knew that would happen. I made this too big, but this is now the S-plane to Z-plane mapping. We have two different or two distinct complex planes. An S-plane that's complex, has a real axis and an imaginary axis. We have a Z-plane that likewise has a real axis and an imaginary axis. And we would like to know if we are someplace in the S-plane, and in particular last time I think we located a pole or a value at a location -3 plus J2, and we would like to know where's that going to map in the Z-plane. I think based on your previous answer, if we had that X anywhere in the left half side of the S-plane, we know it has to be mapped somewhere inside the unit circle in the Z-plane. We derived last time based on a particular closed loop bandwidth. I think I gave you a 5 radians per second. We used that to derive this sample period, this capital T, where T is related to omega sub s, the sampling frequency in radians per second, which is 2 pi over T, and we could then solve for this capital T. Last time I believe we derived that to be, or computed that to be 0.04. Let's then see where that actually places us. I'm not sure that we actually found that location last time. But we did derive that, or sort of explain where this relationship might come from. Z, the complex variable Z associated with discrete time systems, is e to the st, where s is this Laplace variable. We can now replace s with this specific value, this complex number of minus 3 plus j2, which could correspond to a pole location in a transfer function, or it could correspond to a pole location for a pole of a waveform, and then t, the sample period we said was 40 milliseconds, or 0.04. And this gives us then two pieces. It gives us a piece that's minus 3 times 0.04, or minus 0.12, and it gives us another piece, e to the j 2 times 0.08, or 0.08. And remember that this is in the form of radians as far as an angle is concerned. If we compute these numbers, then that gives us a radius, an r, and an e to the j theta. So if I wanted to, I could say, oh, that's r e to the j, let's say theta sub d, and the r in this case is e to the minus 0.12. That ends up being 0.887. And if I convert that 0.08 radians into degrees by the scaling factor of pi over 180 or 180 over pi, depending on which way you're going, in this case, which way would it go? 180 divided by pi times 0.08 would give us the angle in degrees. If we do that, we end up with a pretty small angle of 4.58 degrees. Here is then our radius, or this is now a polar form representation of this complex number z, and this is our angle. And that we can now go up here and insert, if we say that's 1, and if I'm quick to say that's halfway between, then there's my tick marks between that, and I need to be almost at 0.9 and an angle very small, less than 5 degrees, so my location in the complex z-plane has an imaginary component. It's at an angle of 5, roughly, and a length, or a radius away from the origin in the z-plane, of about 0.9. So that point on the blue x in the s-plane gets mapped with that choice of sampling period to a location of 0.9 at an angle of 5 degrees, roughly. And that's definitely inside the unit disk. The radius is 0.9, and that's less than 1. So we know that that particular point, which started in the complex left half of the complex S-plane, would be a stable location if it was or corresponding to a plant. Then that mapped into something that was inside the unit circle. So this is now giving us, if we wanted to, say, a location would be stable if it's inside the unit circle. Now, if something is stable, we might be able to talk about settling time. If something's not stable, it would just go unbounded, or it's just there banging back and forth. It's oscillating forever, and it's never settling on any particular value. Let's now talk about a settling time, because we know what can lead to a settling time in a discrete time system. And to do this, we could either say, well, when's it going to get to 1% of our final value, or when's it going to decay to 1% of where we started? It's easier not to force it. We'll just do an initial condition response. Let's then consider an initial condition response, which really says that we don't have any input. And we do have, let's say, if our response variable is y, we do want an initial condition that's non-zero. That would give us a trivial result if we said, what's our system going to do if I start at 0 and I don't excite it? Hopefully you know that it's going to stay at 0. It's just going to sit there at 0. For a first order system, what's the difference equation look like? If I ask you that on an exam and I said, give me a first order difference equation without an input, what would you write down? Did everybody hear that? So the point, or the response, was y of n minus, did you give me a stable system? So the response was y of n minus y of n minus 1 equal to 0. And that's marginally stable, isn't it? That's just going to sit there and continue to be at one location all the time. But let's go ahead and implement or increase the left-hand side argument. Y of n plus 1 is equal to a y of n. That's a first order difference equation. It's first order because we only have one advance or delay in the arguments. And this a, we'll assume that that's a real coefficient. And now if it's going to be stable, what do we know has to be true about a? A needs to be less than 1. And if a was negative, so we could say, let's just make the absolute value of a less than 1. Because if a was minus 1/2, it would decay, but it would oscillate violently back and forth between each sample, changing its sign. It's a little bit better behaved if it's positive and less than 1. If we know this is true, then we can simply iterate or recursively find a closed form solution between the initial condition and some ultimate value of y at some ending point, or what we might consider a stopping point, capital N, in number of samples. Meaning y of 1 is just a y of 0. That's how we defined our system. But we also know then what y of 2 is. By our governing dynamics, that's a y of 1, but we also, from the previous expression, we had an equation for y of 1 in terms of y of 0. And so we get y at time 2, sample period 2, is related to the initial condition by a times itself, or a squared. One more, and then I think we have it, right? So a of 3 is a y of 2, but y of 2, if I sort of skip a step, if I get lazy, that was a squared y of 0. And I think now you can see the pattern, that if we continue with this, if I want to know what's the response going to be, capital N time steps into the future, you can tell me what that's going to be, formula-wise. That's just going to be little a to the capital N times y of 0. And that's our general response in terms of the initial condition and some subsequent value of the output at a future time, capital N. But we can now use this relationship to figure out what a N is that might produce a 1% settling time. Now we're interested in when do we get, in terms of sample periods, within 1% of where we started? What do we want to have happen? What do we want y of capital N to equal? If we want to make y of capital N equal to 1% of y of 0, we just multiply y of 0 by 0.01. So this is now 0.01 y of 0. What are we doing pictorially? If you can, so here is time. We start at some y of 0. We are saying we want to know when do we get within this tube and stay there for all subsequent time. This is now 1% of our initial condition. Or this is now, and this would be minus 0.01 below that if we had some ringing going on. In a first order system, we're not going to get ringing. But we could define the settling time for a second order, and it might now ring. We want to know if it's ringing, when does it first get inside this tube and remain inside that tube? What we're doing now is really just a exponential response. And we want to know what's the time that we may settle. And it may happen, let's say this is our capital N settle, and this is now N settle minus 1. Maybe N sub settle is 20, and we actually get in that tube between 19 and 20. We would kind of have to over-specify the sample period because we only are measuring this at sample periods, discrete sample periods. Meaning we might calculate a value that says, oh, N is 19.27. Well, we have to say if you want to get within 1%, you have to go to 20 samples. You have to go beyond that fractional sample period or amount. We now know, though, that we wanted to compute this capital N. We convinced ourselves that this is what we want, but we also know that y of capital N, from our inspection of that process, that recursive process, gave us this relationship. And if y of 0 is non-zero, we can divide it out on both sides and end up with 0.01 equaling a to the n. And if we know little a, the only unknown in that is capital N. And this is why we learned our logarithms, right? Now we can solve for N, which is the number of time steps to settle to 1% of our initial value. Questions on that? And if we did this, we could do it all sorts of ways. If we used base 10 log That might be easier for 0.01, since that's 10 to the minus 2, and we can take that base 10 log pretty easily, but we know that's now log base 10 of a to the n, but now we can use our properties of logarithms and say, oh, that exponent can flip out in front of the log, and now we can just compute log base 10 of a, whatever a was. What's log base 10 of 0.01? Minus 2. Or if you don't see that, you go, wait a minute, I can just rewrite this as 10 to the minus 2, and now I can do that trick that I just did. The minus 2 can go out in front, and I know log base 10 of 10 is 1. So now I know that I have minus 2 is equal to n log base 2 of a, or n is now this minus 2 over the log base 10 of a. And if we use our particular a that we had, which was not a first order system a, but it was the radius away, that's okay. That's really telling us how quickly we're contracting. That was this 0.887. You do the math, and that tells you that n is now 38.4 samples. Or the system transient, where the transient is saying it's going to be gone after when we get to within 1% of where we started. The system transient will take approximately 38. We could round up to 39 if that's what we need. So we could say 39 sample periods. And you go in, you just go into your boss and you go, I know the settling time. It's 39. And they go, I don't care 39. What's that represent in real time? How long is your settling time? I don't care how many samples it is. 39. Who cares? How do we figure out the actual time that it's going to take to settle? Pardon? Right. What was our sample period? We need 38 of those or 39 of those to settle. And that's how we would give them that particular result. We would say, oh, we were sampling at 40 milliseconds or 0.04 seconds. Meaning if somebody wanted the actual time value, you could say, okay, the settling time is that n that we just calculated times our sample period t, which is, oh, and I calculated it for, well, I can do that, I guess. I calculated it for 38, but I can add in another one maybe in real time. Just add 0.04 to my old answer, which was, so it takes us about 1.5 seconds to settle in real time for that particular example. Are there questions on how to compute the settling time, the 1% settling time for a first order system? Is that clear? And now you know how to compute the actual time to settle in seconds.
Y of n plus 1 is equal to negative 5.
So the question was, I said there wouldn't be ringing in a first order system. I should have qualified that and said if my first order system has a value a between 0 and 1. If we allow a to be negative and still have a stable magnitude, which means a has to be less than 1, A could be minus 1/2, and then it is going to be bouncing back and forth. And so every other sample, if we did that, here and I can't draw this properly because how many points would I have to include? I would have to get 38 right there. I'm not going to try to do that. Okay? So I would probably be off. That's why I said you guys need to take art, because you can do that then in your art class. You can draw circles and lines, right? And make a nice shape. Where was I going with that? Oh, so now if you have an A that's negative, you might happily start here, but where's the other one going to be, the next one? It's going to be down here, the same distance that one was up. And then what's the other one going to be? It's going to be right here. And then it'll be here. And you'll just bang back and forth until you reach that. This will be the same, your sample, but you will have ringing back and forth for a first order. But a second order, you might have something that looks a little more interesting or nice. And you didn't see that on the video. That's why you come to class, right? So you can see that trajectory. You can hear it maybe, pick it up on the mic. Then you can visualize what that is, just from sound. Questions? Yes? No? All right. Now, let's talk about, we've gone from many different places. Let's do another example where we actually go from time domain difference equation into the frequency domain or the Z domain. And I think we've hinted at this, but let's look at converting a time domain linear difference equation into the Z domain so that we can find a transfer function. Let's start with the difference equation. Y of n plus a sub 1 y of n minus 1 plus a sub 2 y of n minus 2 plus a sub 3 y of n minus 3, oh, I'm getting tired, equals b sub 0 u of n plus b1 u of n minus 1. And we want to take this is a time domain difference equation. What's the order of that difference equation? Anybody have a six-sided coin? Or some dice? So you guys are playing dice out in the hallway, is that right? Okay. Somebody was playing something out there. Maybe it wasn't dice. Maybe it was chess. All right, flip a chess piece. How many, what are the, what's the order? How many delays or advances do you, so here what you do is you concentrate on the output. Like in a differential equation, if you had a differential equation relationship between input and output, you would be focusing on how many times that output was differentiated. here we're looking at how many delays or advances do we have in the output, and you see that we have, what, 1, 2, 3 delays. This is a third order system. So if we get this into the frequency domain, into the z domain, that denominator is going to be z cubed, unless we have some cancellations between the denominator polynomial and the numerator polynomial. But this is a third order linear difference equation. And now what we want to do is we want to take that into the z domain so that we can write it as a transfer function. We can get y, capital Y of z divided by capital U of z. What we want to do then is use what we've said we know, and that's supposed to be a script z if you can't read my writing. We're going to just say if this is now, if we take the z transform of little y of n, we're just going to call that capital Y of z. This is pretty easy, right? You give me a y of n, I can give you a capital Y of z. What else do we know? We also know, well, that's getting even worse, isn't it? But this is now y of n minus 1, or sometimes we may or may not suppress the sample period. This is also, we could write it that way if we explicitly wanted to include the sample period. A lot of times we just neglect it and say this is the output y at time little n minus 1. N minus 1 time sample periods into the future. So t may or may not be there. Hopefully that's not going to confuse you. But then what does this look like in terms of capital Y of z? That's what we said we were using for z inverse, wasn't it? This is now z to the minus 1 capital Y of z. This now allows us to immediately z transform that difference equation, just like we could very quickly Laplace transform a differential equation, a third order differential equation. And if we're looking for if we're looking for transfer functions, we don't have to worry about initial conditions. We're just looking at the behavior of the system. So now what's my result going to be? The very first term was just little y of n. That's just capital Y of z. The next one, bless you, was little y of n minus 1 scaled by a1. Then I had some more. And this is all on the same line. But I didn't want to upset you and do my infinitely scroll to the right. So this is now a sub 3 z to the minus 3 y of z equaling b sub 0 u of z plus b1 z to the minus 1 u of z. Is that okay? Where that came from? Now we can factor out the common z transformed quantities on either side, and we can now say we have 1 plus a1 z to the minus 1, a2 z to the minus 2, a3 z to the minus 3, that's times y of z, equaling b sub 0 plus b1 z to the minus 1. And now we can find our transfer function. We can do the necessary cross multiplication. We can put y, the output, over u, the input. And that leaves us then with b sub 0 plus b1 z to the minus 1 over 1 plus a1 z to the minus 1 plus a sub 2 z to the minus 2 plus a sub 3 z to the minus 3. And maybe you're not comfortable playing with z's with negative exponents, but you can. We can use, have to come early if you get these jokes. Oh yes, I was getting distracted. So now we can factor out a z to the minus 3 downstairs and upstairs to get this in terms of positive exponents of z. Meaning, if I now factor out a z to the minus 3 downstairs, then to get 1 back, I have to scale it by z cubed. And now upstairs I have what? B sub 0 times z cubed plus b1 z squared. And that's now an equivalent transfer function. But now it's written in terms of positive exponents on z. Yes? The question was, on a test, what do I prefer? I just prefer the correct answer, and either answer is correct. That dance around enough? The answer? I think I would, well, it depends on my mood, I guess. If you somehow were being smart or cute, I might just take it all off. But yeah, I'll probably count either one correct. Where was I? Oh, so now we're playing with this z a lot. Let's go back and define a z transform before we get even more buried into these z's. Anybody got z's coming out of their head yet? Not yet? Okay. It's not that late? Or you just had your coffee or caffeine? Let's define the z transform. And before we do that, let's just remind ourselves of what we've, I hope, already been comfortable with, which is the Laplace transform. What's the one-sided Laplace transform? In terms of a generic waveform, continuous time waveform, little x of t. Do you remember what that equation looks like? So what are we doing? We are actually taking our time domain function or waveform, little x of t, over all this time horizon. We're weighting it by this kernel or this complex exponential and integrating that over all time to boil down the frequency content in that signal, or the S domain or the Laplace information in that signal. Meaning we are weighting now this time domain signal, little x of t, by some kernel that's e to the minus st. And that kernel actually weights all of x of t. And we're integrating over all time. But this sort of looks familiar, doesn't it? If I specialize that to one time instant, if I said e to the minus s capital T, that kind of looks like our z, doesn't it? That was like our z to the minus 1. So that's actually what we can sort of think of when we see this z transform. So now if we say, well, what's this Z transform look like? Now we don't have a continuous waveform x of t, we have sampled, or a sequence of numbers that are representing little x of t, or little x of n, actually. So we can put that here. But now we're going to weight that by a kernel that's similar, but that's just one, and we want to do this for all time, so that's now z to the minus n. And we don't need to integrate with these sequences of numbers. We can sum. And that's now our definition of the Z transform. This is, though, just one side. This is just worrying about positive indices on the time index, little n. So this we could say is one-sided or right-sided. It's the positive values of the time index, or that's n greater than or equal to 0. You might see this, and we will see this. We might use the two-sided Z transform. Capital X of Z could go all the way back to minus infinity in n, and now we have x of n, z to the minus n, the same structure, but this is now the two-sided. And this is when n can live for any negative and positive indices. That's our sequence that we can now Z transform. This is now what we want to be able to use to compute these x of z's of, let's say, typical waveforms. So let's look at some common waveforms. And how common could we get? Let's start with the unit pulse. And this you can compare to the unit impulse in continuous time, but now this looks a little bit nicer maybe in terms of believing what this is. This is now the unit pulse. Let me say that's x sub a, since this is waveform A. This is simply going to be 1 when the time index is at 0, or when this argument is 0. So I could shift this around and make it x sub a of n minus 4, and then that would only occur at n equal to 4, for example, and it's equal to 0 for all other arguments. As far as a time picture, I meant that to be blue. That's what this unit pulse looks like. It's just 1 right at n equals 0, and it's 0 everywhere else. And we want to know what's its Z transform. Well, we can just use the definition, and let's just look at one-sided for now. And if we don't really pay attention, we can say, okay, that's x sub a of 0, z to the minus 0, plus x sub a of 1, z to the minus 1. And these are just, what? These are just delaying me one in time, effectively. That corresponds to what's happening in one time unit, 2 time units, 3 time units, etc. But knowing what we know as far as little x sub a of n, the only non-zero term is x sub a of 1. So the z transform of that waveform is pretty easy. The z transform of the unit pulse is just 1. And that's true for all values of z. It didn't matter what z was, did it, to compute that. It converged, that sum, it converged because it was just 1. It was a bounded number. So that was well behaved. It didn't matter what the z was. Z to the 0 is 1, and x sub a of 0 was 1. We get 1. That one was pretty easy. Let's look at the unit step in discrete time. And this one you can quickly sketch because you've had your art class, right? This is now 1, 2, 3. And I'm drawing the stems on here just so that you realize it's nothing in between. Ooh, that's supposed to line up. You guys have your art class. That can actually be right on that tick mark. And that's level. That's a unit value, 1. And I might show this continues by these 3 dots. So that now x sub b of n is equal to 1 for all n greater than or equal to 0. Okay? So now we want to take the z transform of that. That's the unit step. So now we say, well, let's just use the formula. We know capital X sub b of z is this sum, and maybe we don't know better, so we say, oh, we need to use the full-blown version of the z transform. Let's try the two-sided. That's x sub b of n, z to the minus n, but then you go back and you go, oh, that doesn't have any non-zero values for negative n, so I can eliminate half of those. So I can now say this is the sum from n equals 0 to infinity. Are we okay there? And this is just 1. So now I have x sub b of z is 1 times z to the 0 plus 1 times z to the minus 1 plus 1 times z to the minus 2. Man, my world. Does that look like a Laplace transform that you've done before? Just a string of s's? No, not really. Well, let's look at what we've seen before. So let's go back and look at the unit step in continuous time. And so now you need to know by context whether that u of t or u of n is an input generic waveform or whether I'm using it to represent the unit step. You'll have to just know that by the context. In the continuous time case, that's what we have. Now, if we transform that, what's the Laplace transform of the unit step? 1 over s, isn't it? So now we could sketch a pole zero diagram in the s-plane. Where are my finite zeros? What values of S, finite values of S, cause capital U of S to vanish? Finite values of S. There are none, right? The numerator, there's nothing, no polynomial in S. There's no finite value of S, so we don't have any finite zeros. Do I have any finite values of S that cause that to go to infinity? Zero. So I do have a pole, and it's right there. So that's now my pole zero diagram in the S-plane. This is now the time domain, and this is the frequency domain. And that's the unit step in the continuous time setting. And our time domain in the discrete time didn't look much different. It was always 1 for each sample period. So is our pole zero diagram, is our frequency domain plot or picture going to look something like this? So now we have 1 plus z to the minus 1 plus z to the minus 2 plus z to the minus 3. We can just keep walking. I don't even know which direction I'm going. South pole, right? Isn't that south? Yes, okay. So go south. But we don't want to go that far south. But the tail never ends, does it? But we've had a strategy for finding these sums if it's well behaved. And this is just a geometric series, isn't it? Each of these terms differs by the previous one by a ratio of z to the minus 1. If I look at this term, this z to the minus 2, that's just z to the minus 1 away from the previous one. And so I'm just changing each of these terms that I'm adding by a ratio of z to the minus 1 each time. And that's a geometric series. So let's see if we can find a closed form expression for that infinite sum. We have x sub b of z is 1 plus z to the minus 1 and do you remember what you've learned from your math classes on a geometric series? When would this sum be well behaved? Or when does it give you a bounded result, adding up this infinite number of terms? Or when is that finite? So as long as this ratio, z to the minus 1 is less than 1, that's going to be nice, isn't it? That sum. So this is going to be well behaved or nice as long as this is true. So let's just kind of keep that in our pocket. So now we know that as long as z to the minus 1 is less than 1, this tail, these terms are going to get smaller and smaller, and it's going to be well behaved when we start adding them up. So this is going to be a bounded result, and if that's the case, then what if I just took x sub b of z and scaled it by z to the minus 1? Then what do I have? I then have 1 times z to the minus 1, which gives me z to the minus 1. I have z to the minus 1 times z to the minus 1, which gives me z to the minus 2. And I just keep going. The tails look the same, don't they? I can now compare those or take their difference. On the left, I have capital X sub b of z, and I subtract z to the minus 1 x sub b of z, and I can make that look that way by factoring out the common capital X sub b of z. And now if I take the difference on the right-hand side of that equality, what do I have? 1. That's the only term that's different on those right-hand sides. So now I really have my result. I now know that my z transform of this unit step is 1 over 1 minus z to the minus 1, as long as my sum converged, and that's going to happen as long as that ratio, which I found was z to the minus 1, is less than 1, or 1 over z, absolute value, is less than 1, but that's the same as saying, can't write up against the wall. The absolute value of z, as long as that complex number is bigger than 1, that sum is going to converge, and I'm going to get this for my z transform of a unit step. So I have a unit step that's well behaved as long as z, this complex number, is bigger than 1. But I could do my strategy for writing this in terms of positive exponents like I've done before. I can factor out a z to the minus 1 in the denominator from both terms. This now says that x sub b of z, I could write that way, but that's just z over z minus 1. And that's true as long as z is bigger than 1, or it's outside the unit disk. And that's now my z transform of a unit step, gives me this ratio of polynomials in z, z over z minus 1, and we sort of call that condition the region in the complex plane where we have convergence, or it's called the region of convergence. And you might see that depicted then. Here's my z-plane, and I now need to shade in that z-plane all values of z that allow this transform to exist or to converge. And in this particular case, for the unit step, I needed those z's to be outside the unit disk. And this is now my region of convergence, which is just this guy. That condition said, oh, z needs to be outside 1 in order for this sum to be bounded, and if that sum is bounded, then I can write it as this closed form expression, or this ratio of z's, as z over z minus 1. And that's now my z transform of a unit step. And if I wanted to, I could now compare that with what I had in the continuous time case. In the time domain, I had something like that. Now, in terms of the z-domain pole zero diagram, what do I have? Do I have any finite zeros? Do I have a finite value of z that causes capital X sub b of z to vanish or to equal 0? 0. So now my pole zero diagram in the z-plane actually does have a 0, an open circle, right at the origin. And I have a pole. Where's that pole? Right at 1. And this now, that's a signal, or it could represent a system with this relationship between input and output, and that would correspond to something like an integrator. You're just summing things up. And so if you applied a unit step to an integrator, what's going to happen to the result? It's going to go unbounded, isn't it? Just like if you applied a unit step in the continuous time, a 1 over s, to an integrator, which is 1 over s, you have 1 over s times 1 over s, which gives you 1 over s squared, which the inverse Laplace transform is t, and that's just going unbounded. And this is consistent with that observation. If you go back here, where is this pole in the S-plane relative to the stability boundary in the S-plane? Where is my stability boundary in the S-plane? My boundary is this imaginary axis, isn't it? I need to be to the left of that to be stable. So that pole is right on the stability boundary. Where's this pole? My stability boundary is governed by the unit disk. It's right on the stability boundary. Again, we're consistent, aren't we, between the continuous time and the discrete time systems or concepts. Questions on that? Well, this is kind of fun. Let's just keep going. What have we done? We've done 2 waveforms. We've gotten to B. We need to learn our ABCs. We need to... Okay. Question? So the question was, can we map between the S-plane and the Z-plane? And most of the time, we will be assuming that's the case in this class. So I'm not quite sure what you're asking, but we should be able to, if we had a continuous time waveform, we can sample that waveform and get a sampled signal, which we could then think of as a discrete time signal. Once we have a discrete time signal, now we can Z-transform that and get into the Z domain. Or we could say, well, I want to play in the continuous time. I'm going to stay with Laplace. Somebody goes, well, I need you to design a controller in a computer. You go, now I have to go into the Z-plane, maybe, to design that controller. You need to work in the discrete time so that you can give somebody a difference equation and they can go code it up into their machine. And now it'll sit there and crank numbers and do the filtering or the controlling that you need it to do. All right. Did that help answer your question about S and Z? Now what I want you to do is get comfortable with going between the two. If I give you something in the S domain, where does that map in the Z domain? And everything in the complex left half plane of the S better go inside the unit disk. That's the corresponding stability regions in the 2 different planes. The complex S plane is infinite in extent, isn't it? In the Z plane, it's not. What's the area of a circle? Pi r squared, right? What's the, oh, another pi. Yeah, it's getting close. I had cake before I came to class. I don't think we have a cake symbol up here, but I might start writing it down. Anyway, don't tell anybody. I'll be telling you, I guess, and if I keep having cake before this class. By the end of the semester, I'll have 10 more pounds. Snickers? Oh, don't show me that. Where are we? Pi. Oh, yeah, the pi. Now, if we, and that's now, we have to worry, now we're crammed into a smaller, we're crammed into a finite region in the z-plane for stability. Where are the stability boundaries? This is the imaginary axis. That's our stability boundary in the s-plane. If we now have z equaling e to the st, but now if we let s be just j omega, the imaginary axis, now we have z is equal to e to the j omega t. Where's that going to put us? Now our frequency response is going to be looked at based on this perimeter of our unit circle. That's the stability boundary, and that's how we will evaluate the frequency response. If we need to, we'll evaluate things on the unit circle. Let's now continue with another common waveform. Let's say it's the exponential. So now this is r raised to the nth power, and let's just consider one-sided, positive values of n for tonight. Well, that could actually represent two different waveforms, couldn't it? We could have something that looks like that. Let's say we're starting at 1, since I didn't put any kind of scaling factor in front of that. So at n equals 0, r to the 0 is 1. We'll start at 1, and we'll just exponentially decay as n increases. Here's n. There's our time. And this is really, and those are supposed to be equally spaced. What's the value of r look like if we have this decay? What's the magnitude of r look like? It's going to be less than 1, isn't it? But we could sketch that's also x sub c of n, isn't it? But now r, in this case, it's actually positive, but it could bang back and forth if r was negative, but it's now growing if r is bigger than 1. Is that okay? Now, to connect this with what you already know, again, sort of continuous time and discrete, here's a little adventure. Let's do an aside. We can actually say, well, I know what a exponential looks like in continuous time. That's maybe this e to the minus at for t greater than or equal to 0. What if I sampled that, though? What am I doing when I sample? I'm simply replacing t, or only looking at that continuous time at certain instances, right? And they're one sample period away. They're capital T units away from each other. If I sample that, that's just like replacing little t with little n capital T, where capital T is the sampling rate, or the sample period, I should say. So that this now becomes x of nt. But that's now just e to the minus a nt, e to the minus ant. But x of nt, the sampled version, now we want to play a little bit with that n. N is the only thing that's changing in that exponent. A is fixed, capital T is fixed. So let's now, that's the same thing, isn't it? But I could just say, oh, you know what? You give me an A and a T, and I'll give you a number R. So that's just R to the n. That's where this exponential shape you can sort of think of consistent with what you're used to seeing in a continuous time exponential. So that's consistent with r to the n. Is that okay? And that's going to be for, let's say, n greater than or equal to 0. So that's why we can call r to the n an exponential, is another way of justifying that. Let's now find the z transform. That's capital X sub c of z, which is this sum from 0, little n equals 0 to infinity, little x sub c of n, z to the minus n. That's just x sub c of 0 plus x sub c of 0, whoops, x sub c of 1, z to the minus 1, plus x sub c of 2, z to the minus 2, and that just keeps going. But that is now 1 plus r, z to the minus 1, plus r squared, z to the minus 2, plus r cubed, because that was what we said x sub c was. That was r to the n. But we know how to do this. We just have to identify a common ratio, and then we have a geometric series again. So if I now say this is 1 plus r z to the minus 1 plus r z to the minus 1 squared plus r z to the minus 1 cubed, now I know what my ratio is. It's this r z to the minus 1. And when is that going to be well behaved? This sum converges when what happens? I need to just find the ratio between those different terms, don't I? And that's just rz to the minus 1. And I need that to be less than 1 in magnitude. So this is going to converge as long as r z to the minus 1 is less than 1. Now we can do our trick that we learned maybe even in the first lecture, right? Except then it was finite series. Now we have an infinite series. But we now know that we have capital X sub c of z is 1 plus r z to the minus 1 plus r z to the minus 1 squared, etc. Now we just hit that with that common ratio, and now we have what we're used to seeing, or this now becomes 1 minus r z to the minus 1 capital X sub c of z is equal to 1. Or the z transform of an exponential, discrete time exponential, or, and when is that true? That's true as long as r z to the minus 1 is less than 1. Well, that's just r over z less than 1, or that's just z having an absolute value bigger than r. R is now going to define a disk in the z-plane, and our radius or our region of convergence needs to be outside of that. We can now sketch this. Oh, that's supposed to be centered at the origin. I told you I didn't take an art class, but what's the pole zero diagram look like? This is now our z-plane. Do I have a zero, a finite zero? It's at the origin, isn't it? Where do I have any finite poles? I have one at R, and this is not the unit disk. This is a disk of radius R, and this is now outside of that. Wow, that's pretty bad. This is my region of convergence. Now, I haven't said anything about stability. I've just said that that particular sum converges. And R could be less than 1, it could be bigger than 1. The region of convergence is just having to be outside of that R. And then I get this particular result for my Z transform of an exponential. Questions on that? So we will look at exponentially damped cosines and sines, and then we're pretty much good to go with Z transforms. We'll do that on Monday. Don't forget your homework is due Thursday, tomorrow.